On the left side of this split screen, a single API request processes for fractions of a cent. On the right, a company's monthly cloud bill rapidly ticks into the millions of dollars. To understand the gap between those two numbers, we have to separate training from inference. Training a massive model requires millions of dollars of hardware and energy upfront. It is a massive capital expenditure. Inference is the operational expenditure. It is the cost incurred every single time a user submits a prompt and the model generates a response. In traditional software as a service, scaling relies on a specific economic principle. As you add more users to a centralized database, the compute cost per user approaches zero. Large language models break these traditional software scaling rules. The unit economics of an LLM are bound to intensive GPU matrix math. The more users interact with the system, the more math is required. We are going to trace the exact life cycle of a prompt from software tokenization down to physical hardware execution, and then map that physical reality directly to SaaS profit margins. Managing this physical to economic pipeline allows technical leaders to scale user growth without eroding their margins. This 3D framework separates AI costs into 3 layers: hardware clusters below, software in the middle, and business metrics on top. Starting in the software layer, the model performs tokenization, breaking text into sub-word pieces. These pieces are mapped into high-dimensional mathematical vectors. The system triggers the transformer's core engine, the attention mechanism. It mathematically multiplies these vectors against every other vector in the sequence to establish context. This generates a single new token, halts, and feeds the sequence back to the start. The system cannot generate paragraphs in parallel. It must stop and recalculate the mathematical sequence for every single new word it creates. This process dictates the pricing disparity between input tokens and output tokens. Output tokens cost more because they force continuous data movement and constant context recalculation. Input tokens are processed once. Output tokens force a continuous loop of heavy computation. The architectural design that gives the transformer its ability to understand deep context makes it an economic liability at scale. To find out where the money actually goes, we drop down from abstract software logic to the physical execution layer. The transformer's vector multiplication translates directly to continuous matrix math operations on the GPU. A misconception is that processing speed limits hardware. The true physical constraint is memory bandwidth. Financially, the largest cost slice is hardware amortization of expensive TPUs, followed by enormous electricity and thermal cooling costs, and finally, high-speed networking to synchronize multiple nodes. Cloud providers pass every cent of these physical inefficiencies directly down to the AI application developer through token pricing. An API call is a physical event that leases millions of dollars of hardware infrastructure for fractions of a second. Moving to the highest layer of the framework, we see how hardware physics impacts the boardroom. In a standard SaaS application, the monthly recurring revenue per user is generally fixed by a subscription tier. Now consider a growth scenario where users increase their engagement with the AI features of the platform. That increased engagement forces the generation of massive amounts of computationally heavy output tokens. The variable inference costs rise linearly, or even exponentially, intersecting and climbing above the flat subscription revenue. This dynamic explicitly crushes gross margin. Every additional action the user takes costs the business money. The ripple effect destroys the contribution margin once other variable operational costs, like customer support and server hosting, are factored in. Traditional venture capital playbooks prioritize user growth at all costs. That strategy fails here. Subsidizing AI users simply means subsidizing NVIDIA hardware. Rapid user adoption of a poorly architected AI wrapper actually accelerates a company's path to bankruptcy. This is the critical failure state. Unchecked hardware strain destroys the SaaS business model. Because you cannot change the underlying physics of the GPU, the engineering mandate is clear. You must architect a smarter token flow pipeline. The first optimization is semantic caching. Repetitive queries are served directly from a database, bypassing the expensive hardware layer entirely. Next is prompt compression, which minimizes the number of input tokens that require processing by stripping out unnecessary context. Implementing retrieval augmented generation, or RAG, injects precise, relevant data into the prompt. This eliminates the need to push massive, generalized documents through the context window. Finally, model routing analyzes the complexity of a prompt before assigning it to a model. A router directs simple classification tasks to tiny, inexpensive models. Heavy GPU compute is reserved strictly for complex reasoning. In aggregate, this pipeline optimization reduces the physical hardware load. Connecting this optimized hardware load back to the boardroom, the variable cost curve drops well below the revenue line, restoring a healthy gross margin. AI engineering is shifting from prompt writing to rigorous systems architecture. The true intellectual challenge of modern AI is building an architecture where the unit cost of inference remains lower than the revenue it generates.